Good morning, Abyssers. Welcome to the final episode of AP Calculus AB. BC, the extended version, is still going on, so feel free to check in at an earlier time than now. Okay? So, for those people that are taking BC next year, by the way, you could get a preview by watching the archived live streams and just see a little bit what is the chaos about. So anyway, so I'm going to start way in the back this time with Zach. Okay, we're going to talk about something called L'Hopital's rule, which is just kind of a nice little shortcut to take limits. And we're also going to talk about something about indeterminate forms, which you need to know to be able to use L'Hopital's rule. So anyway, we're going to just do a little review of limits. Okay, so the limit as x approaches 2 of x. I'm not trying to trick you. I think you said 2. Is that correct? That is the correct answer. All you got to do is put the 2 in there and you're done. Manu, what about this one? Can I put 2 into there?
No.
If I put 2 in there, I'd get 0 over 0, right?
Yeah.
Which, by the way, is an indeterminate form. Okay, 0 over 0, that's what we call indeterminate. So what would you do, Manu?
Factor out x squared minus 4.
Okay, just wait here. You'd factor this?
Yeah.
What does it factor to?
X plus 2x minus 2.
That is perfect. That's very good. What type of relationship do x plus 2 and x minus 2 have? They're what? You remember?
No.
They are conjugates. Okay? Or what my sister would call the evil twins. Okay? That's not true in mathematics, but it's true in my family. So, what would you have me do, Manu, now that you factored those?
Cancel out x minus 2.
Yeah, these would simplify. And so pink is kind of a kinder red, I think. And now can I substitute?
Yeah.
What do I get?
4.
4. Perfect. And that would be what we're approaching on that function. Jacob,
Yeah.
what would you do here?
You would multiply the top and the bottom by square root of x plus 2 plus 2.
Wow, that's very good. Like this? Okay, what's the relationship between these two?
They're conjugates.
They're conjugates also, okay? So that gives me the limit as x approaches 2. What do you get when you multiply these conjugates?
You should get x plus 2 minus 4.
Perfect, okay? And down here I'll have x minus 2, parentheses, square root of x plus 2 plus 2. Does that look correct, Jacob?
Yep.
Okay, can you see that okay in the back? Jacob?
Yeah.
Okay, so what is x plus 2 minus 4?
Minus 2.
What?
X minus 2.
So that's x minus 2, and this is x minus 2. So those will be removed.
Yep.
What would be left in the numerator?
1.
1. So now I can substitute a 2 in here.
Yeah.
And 2 plus 2 is?
4.
And the square root of 4 is?
2.
And 2 plus 2 is?
4.
And so I get 1/4 as my limit?
Yep.
Perfect. Awesome. So we've learned either direct substitution, factoring and simplifying, multiplying by a conjugate because we got square root, right? Those are all techniques in finding limits, right? And L'Hopital's will be another technique. But before we get to L'Hopital's, this one right here, Emily. You know what? We don't even need to factor. You remember both of them are quadratic or have a degree of 2, right? They're identical. So I would look at the leading coefficients. Do you remember that?
Yeah.
So what would it be? 1/3. Okay. Right? I could simply look at those leading, right? The biggest exponent. And so that's another technique. Do you remember doing that? I think they also do it in pre-calculus, don't they? All right. So for some that we're not able to do, we're going to use L'Hopital's rule. And there are 2 types of indeterminate forms. We're only going to worry about the first group. When we get into BC Calc, we worry about the second group. But right now we're only worried about that group. So the group is always in fractional form. You have 0 over 0, and the rest of them is some form of infinity over infinity. Okay? And somebody had asked, I thought pretty astutely, second period Maggie, that, well, why isn't infinity over infinity 1? Right? I mean, that's kind of that was my natural feeling. And I said, okay, well, not all infinities are the same. Because let's say you have the real numbers. So that's all numbers except for those that include I. Would everybody agree with that? Okay, and there's a lot of them, an infinite number of them. Okay, Maggie, you remember the whole numbers?
Yeah.
Okay, do you know the difference between the whole numbers and the natural numbers? Okay, so when you teach a baby to count, okay, or a toddler to count, guess what number you start with? 1, okay? Because 0 is a very difficult concept for a toddler to understand. Like you might hold up 1 finger, right, and say 2 fingers and then 3 fingers and so on, right? So they're called natural numbers because in nature it makes sense to think that way, okay? Whole numbers just mean they include 0, right? How many are there of them? How many whole numbers are there? Okay, what would we say mathematically? There would be an infinite number of them, right? So which would have more, real numbers or whole numbers? There's more whole, so they don't include negatives, do they? The real numbers would, right? So those infinite numbers are restricted. You understand what I mean? By either their definition or what creates them. Is that going to make sense? All right. So L'Hopital's rule only applies to the first group. And L'Hopital's rule is kind of neat. It says if you determine that when you take a limit that's in this form, in one of these indeterminate forms, you're allowed to take the derivative of both the numerator and the denominator and look at that limit. And if it's still in indeterminate form, take the derivative of that one until you can draw some conclusion. One of the conclusions is that it has a limit, and the other conclusion is that the limit does not exist. All right? So again, what I've kind of ovaled right here is the indeterminate forms we're going to focus on. So this is very important because I had some people get this confused last year, is you are not taking a derivative of a quotient. For that, you would use the quotient rule. What you're doing is taking a limit of a quotient. So that isn't the quotient rule because you're not computing a derivative, you're computing a limit. Does everybody understand that? All right, so the first thing you have to do, and when I grade this, this is what I need to see, is that you've established that you have an indeterminate form. The way I'm going to do that is I'm going to substitute 0 in for x. And I'm going to get this. I'm going to have e to the 0 minus 1 over 0. I get 1 minus 1, which is 0. And I get 0 over 0, which is an indeterminate form. I now can apply L'Hopital's rule. So I'm going to take the limit as x goes to 0. And Maria, what's the derivative of e to the x minus 1? E to the x. And what's the derivative of x, the bottom? 1. So now I'm going to substitute again. And I'm going to get e to the 0 over 1. And e to the 0 over 1 is what, Maria? 1. That's my limit. I'm done. So the limit of this is 1. The next one. You may remember this one. You might have forgotten about it. I did something in the fall called the squeeze theorem. I had a couple people walk, and they kind of kept another person within a certain range, and you end up squeezing two functions towards a particular number. Remember that? L'Hopital's rule works here. So I'm going to take the derivative. Well, first of all, I got to write the sine of 0. I guess I don't want that. The sine of 0 over 0. And Logan, the sine of 0 is 0. So I got 0 over 0. I have an indeterminate form. So now I'm going to take the, or you are, what's the derivative of sine?
Cosine.
And what's the derivative of x?
1.
And so I have the cosine of 0.
Okay, I have a question.
Yes, I'll get back to you in 1 second. All right, I'm ready for you.
If it's on the bottom, why would it be x squared? Since it's to the negative. So it'd be x to the negative 1.
Oh, because you're looking at the function that exists in the denominator. Okay? Not as a function that exists in the numerator. That's a really good question. I've never had anybody ask that before. Okay? If you look at his rule here, right here it says, all right, this is what you're looking at, and you're not looking at it as a product side by side. Okay? Okay. Are you ready to give me the answer to this one? Yeah. And this is 1. All right. Super. Next page. All right, Nevaeh, I'm going to do the same thing on this one. I'm going to plug in 0, and I get e to the 0 minus 1 over 3 times 0 plus 0 squared. And the result is what over what, Nevaeh? 0 over 0. So I can take the derivative. And what will I get as a derivative?
You have e to the x on top, and then 3 plus 2x on the bottom.
Okay, so again I substitute. I get e to the 0. I get 3 plus 2 times 0. And my limit is what?
1/3.
1/3. It also works when you have infinity. So if I have x and x is getting bigger, Raymond, what can you tell me? Where does e to the x approach as x gets bigger?
Positive infinity.
Positive infinity. So I have infinity over infinity. Would you agree?
Yeah.
So that means I can take the limit here as x approaches infinity. And what would I get?
E to the x. And then, well,
Over 1. So what are we going to determine our answer is here? It's going to be infinity, which means a numerical derivative does not exist. Excuse me, no numerical limit. I think I said derivative. I didn't mean to say that. Yes, sir.
Could you determine its infinity just by looking at it initially? Like e to the x is going to always be a larger infinity than just x itself.
Right, and you can look at it as even a rate of growth, correct? E to the x grows a lot faster than x, right? And so if you take a look at those, they pull away, all right? And so in BC Calc, we look at limits quite a bit because we do this thing about convergence and divergence. and we use Morris L'Hopital's rule as a justification or proof that what we believe to be true is true. Does that answer your question? Okay. Jack. Natural log of x, right? It's a logarithm. Okay. So as x gets bigger, you know, like, so I have the natural log of 1, which is 0, right? And then I have a natural log of 10, and then I have a natural log of 100, and then I have a natural log of 1,000,000,000, right? What can you tell me about those numbers? Are they getting bigger? Yeah, they are. They don't grow very fast, but they are getting bigger. So I have infinity as opposed to this, x squared. So I have 1 squared, 10 squared, 1,000,000,000 squared. Is it also going to infinity? Okay. So now you're going to take the limit for me by taking the derivative. What do I have for a derivative on top?
1 over x.
And what about on the bottom?
2x.
So I can simplify that to be what?
Just be 1 over 2x squared.
Perfect, 1 over 2x squared. My guess, Raymond, in the analysis that you did before, this would be the same type of idea. Okay. And what would you get as a limit in this case?
There's 1 over infinity.
Yeah, what is that? So you get 1 over 10, right? Then 1 over 100, then 1 over 1,000,000,000.
0.
It's headed towards 0, right? Number 6, negative infinity. Riley, where are both of those headed?
Infinity.
Yeah, I'm going to write positive infinity because I have a negative sign here this time to distinguish between the two. What about on the bottom? So I'm raising a number to a power. Can it ever be negative?
No. No. Just infinity.
Okay, so I have a negative 4, and then I'm going to make the negative of a negative 4. And then I'm going to have a negative 10, and I'm going to make the negative of a negative 10. It's going to infinity, right? Did you say positive infinity before? Okay. I didn't hear that. That's my fault. Okay. All right, so you are going to take the derivative. And what is that?
2x over negative e to the negative.
Perfect. So now we're going to take a look at this again, and we're going to put negative infinity in there. What would happen?
It would be negative infinity over positive.
Well, you did have positive.
Still.
What?
Would it be negative still?
It'd be negative infinity this time because I got a negative out in front. Okay. So it's still an indeterminate form, which means I can still take the derivative again of the top and the bottom. What do I get here?
2 over e to the I.
And what do you get here?
2 over infinity.
Yeah, what's the numerical? Anytime you have a constant with something that's getting really big. Yep. Noel, there's a typo here because I can't put negative numbers in that thing, so I got rid of that negative symbol. It's not in fractional form, is it? Can you write it in fractional form?
Yeah. We could do the limit of the square root of x over e to the x.
Like that?
Yeah.
Okay. Oh, are they both going to infinity?
Yeah.
So what do you get as a derivative?
One half x to the negative one half over e to the x.
So you got x to the negative 1/2.
Yeah.
Can I write it like this? Is that x to the negative 1/2?
Yeah.
And down here I have e to the x. So this is growing fast. This is growing. And I'm multiplying things that are getting bigger. And then for fun, I'm going to multiply it by 2 and make it a little bit bigger. Right? So what's that head? Oh, I got a constant on top. Right. What's another way? Oh, 0. All right. That's it. Isn't that nice? Remember when we were doing arc sine and arc tangent and integrating those, and I said this was the hardest thing, and you know, you guys had to go through metal detectors before you came in here because I was worried about my life. And I said this is the highest, and isn't this kind of like coming down like really a smooth landing? You go, really? This is all that is to it?
Yeah, no, because this is like basic stuff that we learned early in the year. It's just taking derivatives.
Yeah. Isn't that a nice way to end?
Yes.
Yeah.
It is beautiful.
Yeah. Everything is beautiful. Everything is beautiful.